From Kamp, we're talking about initial value property.
Right. Thanks for the opportunity to talk here. I changed my title slightly. I had initial value problems for quad equations. Quad equations are defined on quad graphs, but there's all kinds of other equations, and they are usually defined on the normal Z2 lattice. So I will also talk about that and also about quad graphs. And also the title, I mean, these initial value problems that I create are not necessarily for integrable systems. So for any non-integrable systems, you would have similar initial value problems. However, for quad graphs, there is something special about integrable equations. So the motivation why I started to look at initial value problems is basically the staircase method which you can apply. I'll come to that, but basically I will be talking about results in these two papers. One paper by myself and another paper with Frank. Actually that collaboration started at a satellite meeting in Glasgow, I believe, of the 2009 workshop. I will kind of describe the results there, and then I will generalize those results and make a conjecture about, a quite general conjecture about initial value problems on the Z2 lattice for systems on any kind of stencil. And I'll illustrate the statement with a system that Sasha pointed me to about a week ago. And then, if there's time, there's a second part, and there will be specifically on quad equations on quad graphs. And there's a preprint that I put up last year. It's there. So you can have initial value problems. We've seen already quite a few in this conference. So if you have an equation on a square, on a quad, then you have staircases. And you can define initial values like that. And any staircase provides an initial value problem. So what you can do if you have an initial value problem, you can impose a periodicity condition. So if, where's the pointer? In the middle? Oh, there. So if you impose periodicity, so this point would be the same as that point, for example, then you reduce your system to a finite dimensional map. And the staircase method is a method that enables you to use the Lex pair of your equation to find integrals for this map. I won't say much more about that. But there was this initial paper, and this is the first staircase for which this method was developed. And then in a later paper by Quispel, Capel, Naev, and Papageorgiou, it was shown that you can have arbitrary staircases like this one, where the method also works. And this has been some recent work. We've done more general staircases and all kinds of systems, and you can always use the Lex pair to create integrals for the map you get. No significance. No, I mean any staircase will work. Yeah. No, you need the periodicity to use this method. Yeah.
To use the method, but I mean the problem is well posed for any staircase.
Yes.
Absolutely.
Yeah.
No regularity.
Yeah. Also for non-integrable equations, these staircases are fine. These staircases are specifically for equations on a square. But only if you have a Lex pair and you impose the periodicity, then you can create integrals for the map you derive. Only when you have periodicity you're down to a map. Otherwise you're down to an infinite dimensional map if you don't have periodicity. So the way it was done, these staircases, was to introduce a new variable. So here is the new variable, you have S1, S2 periodicity. So S1 will be, say, if that point is the same as that point, then S1 will be 4 and S2 will be 3. And you can introduce that variable, and then if you look at the values of n, then you get exactly the values there. I'll show that in the next picture. So this is an example where you have 2 minus 1 periodicity, and if you look at the values of this new variable n, then if L and n are 0 here, then n will be 1 here, n will be 2 there, and so on. And the periodicity is built into this definition of the new variable. And then the thing I realized is that instead of looking at defining a new variable, what you get is exactly the straightest line on the discrete letters in a certain direction, in the direction 2 minus 1. And that was key to generalize this result to other stencils. So what you do if you have your staircase and your values, you can update the values. You can see the square here. So you can use that square to calculate the new value using the equation. And then you can update these 3 variables here to those 3 variables there, and you're down to a 3-dimensional map. This is how it works. But if you have equations on another stencil, not particularly the square stencil, for example, the discrete Toda equation, if you look at this equation, you see that it's a relation between 5 points, 1, 2, 3, 4, 5. And you have to widen your band of initial values to be able to update anything. So here you would get a 4-dimensional map. Those 4 values, you can calculate that value from the equation, and you have a 4-dimensional map. So in this paper, due to this geometric condition, I showed that you can get initial values for equations on arbitrary stencils. So the main result is that in finitely many directions, for any stencil, in finitely many directions, you would have a Gauss-Sut problem, and in other directions, you have a Cauchy problem. So the initial value, it's a bad sound. So the initial value that John Roberts had, I call that a Gauss-Sut problem. And the staircases are called Cauchy problems. So for equations on a square, there's basically one Gauss-Sut problem, which is this one, having initial values on the vertical and the horizontal line, and in all other directions you would have Cauchy problems. And that is the case for equations on arbitrary stencils. And the directions of the Gauss-Sut problems, that depends on the convex hull of the stencil of your equation. And you always get if you do the periodicity, you always get a map of a certain dimension, and you can actually calculate what the dimension of your map will be, depending on the points of the stencil. So here is a formula, and these DIs that I introduced. So you would have different regions. Here you would have a region R1, and here you would have a region R2, and the dimension of your map might depend on the regions, and it's a piecewise linear function. So these DIs are distances of the stencil. So for the square stencil, DI would be this distance. And you would get the DI by taking a line in that region and another line in that region, and the points where you squeeze the stencil, the points where they touch, that is your distance between the lines, and that's where your initial values will be inside. So if you have a stencil on arbitrary points, you just do the same thing, and you get your DI, and then that's the formula for the dimension of your reduction. And for example, for this discrete Toda equation, you get that this is the dimension of the reduction of your S periodicity initial value problem. So in the same paper, I also did something for one particular system. You can do that. This is the quotient difference algorithm. You can see this is a quotient equation, and this is a difference equation, if you write it with minus signs. And the dimension of its S reduction for arbitrary S is exactly the same as for the Toda equation, which is not a surprise because these two equations, the Toda and the quotient difference algorithm, they are basically related to each other. So then in the work of Paul Spicer in his thesis, he came up with recurrences for two variable elliptic orthogonal polynomials, or actually adjacent polynomials. And from these recurrences, we were able to create a Lex pair. And what also came out was this new equation, a generalization of discrete time Toda on a bigger stencil, like this one. And also related to that was a quotient difference system, and that was a system defined on these stencils. So there's 3 fields, 3 equations, and the different fields are denoted here with different symbols. So one field has the bullet and the circle and the cross, and you can use these stencils to create initial value problems and Gauss problems, and that was done in this paper. What you get is for both the same thing for both the scalar equation and the system. You could show that the dimension of the reduction was given by this formula. Now here is my conjecture, just from looking at lots of systems, and I say that for any system of lattice equations on arbitrary stencils, there's always finitely many directions where we have a well-posed Gauss problem, and in all other directions there is an initial value problem, the Cauchy problem. And here is the example that Sasha pointed me to. Here is the system, but don't look at the system, just look at this, these stencils. There's 3 equations, 3 fields, and the equations do relate those particular points on the lattice. And actually, they had a different kind of initial or boundary value problem. So in a preprint that they put up the web, they had a staircase, a standard staircase for one field, and then there were kind of boundary value problems for the other fields, and that's one way to solve the whole system on that particular parallelogram that was there. But you can create initial value problems for this system and Gauss problems for that system, and I'm going to show you how. So for this system, there's 4 different regions. And you can kind of see where the regions come from if you look at this stencil, because the convex hull of these equations, this involves the direction 2 minus 1 for that field, and there's a direction 1 minus 1 for this one, the same one here. There's the horizontal direction here, and there's a vertical direction over there. So you can see that there's different regions like this where you would expect different ways of producing these initial value problems. The dimension is given here, and it's obtained similar as over there. But it's a bit of it's not really algorithmic. You don't know a priori which stencil to solve for which field, and how you should position the different stencils in one picture. But the result is here. So these are stencils which you can squeeze with lines to obtain your initial value problems, and I'll show you how to do that. So first example, we'll be using this diagram here. What you do, you put your diagram on your lattice, and you squeeze the stencils with 3 sets of lines. So for this field, the bullet field, what you have initial values between this line and that line, not including that line, because you're going to solve for that point on that line. And for that field, you have initial values between this line and that line. And for the other field, similarly, you have initial values between here and there. So what you get is that this is an initial value problem for the whole system. And you can verify that. This equation you use to update at that point. So you would be able to calculate this point from this stencil. But as you can see, you should first update. Well, let me see. You should first calculate the cross on this point. And you can do that using this equation. So you first calculate this point over there. And then you should also calculate this point over there. And then you would be able to use this stencil to find the bullet over there. So there's an order in which you have to solve these equations.
You cannot solve this equation just in the upper part of the plane without solving down.
No, you can start. You can go in two directions. So I just showed you how to update it in this direction. And you should really, to verify that this is all well defined, you should also show that you can update in that direction. Yes. So here's another example, just nice pictures. It works similarly. This is an initial value problem for, in this direction, 3 minus 2. So there's a condition on the lines of the stencil, these two subdirections. You can't have Cauchy problems. So what you do there is, for example, in this direction, you have these initial values, but you need other values in this direction. So this is a good shot problem for that system. And just to be complete, and for you to kind of see what kind of Coursat problems you could have. This is the Coursat problem in this direction with additional fields in some direction, orthogonal or not necessarily orthogonal. But, here we would have a Coursat problem in the, 2 minus 1 direction, and here is the Coursat problem in the other direction. So this describes all the initial value, the Cauchy and Coursat problems for the particular system. Here's an invitation. If you have a system and you want to know initial value problems and Coursat problems for them, just send them to me. This is a way I can kind of maybe, well, first of all, test the conjecture, of course, and yeah, maybe devise some algorithmic way of doing this, because it still requires a bit of thinking. It might be a combinatorial problem, and yeah, it's nice. So one reason of doing these initial value problems is you might want to reduce your system to a map, and then do a periodic reduction and find integrals for that map. But another reason why you want to have initial value problems is basically doing difference elimination theory. So if you want to verify that your Lex pair is really a Lex pair, that the result vanishes on the system or anything, you have a symmetry condition, you calculate your condition, you want to know whether it's 0 or not. What you have to do is you have to have an elimination map. So you take your expression and you have to reduce it onto something where you would know it is 0 modulo the equation. So you have to reduce it onto an initial value staircase or onto a Coursat problem, and that's also an important point I wanted to make. So now I come to the second part, what to do if you have a quad equation and how to define initial values there. So in this preprint, I provide a method to construct well-posed initial value problems. Or maybe it's not clear whether they are Cauchy or Coursat on these graphs, but I just call them initial value problems. Quad graphs need not be simply connected. I'll explain what I mean by that. for non-integrable equations, the graph should not contain closed strips. I'll tell you what the strips are and why you need this. For integrable equations, the graph should not contain self-intersecting strips, and not all quad graphs admit well-posed initial value problems. So the method doesn't always work, but there is a setting where it always works, and this is the setting of rhombic embeddable quad graphs, and we'll see examples of that. So this is a rhombic quad graph, and basically a rhombic quad graph is where all the edges have length 1, and then it means if they don't have you could say a graph is rhombic embeddable if you can kind of transform it into such a graph. I'm just going to show you some examples of quad graphs, and this one has a closed strip. So what is a strip? A strip is basically a line through the edges. So you would start here, then you would go to the opposite edge, and you would go to the opposite edge. That is what a strip is. And as you can see, this strip closes. This strip is open. There's another strip here, and then there's one strip over there. This is a non-simple quad graph. In graph theory, a graph is non-simple if there's multiple edges between points. But this is a perfectly well-defined quad graph. It just has one self-intersecting strip. So if you enter here, you go there, you get out here, you go there, that's the opposite one. That's one strip on this graph. And this is, by the way, the first example of a quad graph where you don't have an initial value problem. So as you can see, if you impose these three fields as initial values, you would be able to calculate this one in two different. You would be able to calculate this one, and then you would be able to calculate that one, and then you still have a relation here, and you might not get the same value. So it's not well posed. This is a non-simply connected quad graph. What I mean by that is that there is a face which is not a quad. But you can still define initial values on this graph, and there's no relation on this face. This is a non-proper one. You need 4 edges on every quad. So here we have a quad, meaning there's 1, 2, 3, 4 edges, but there's no 4 vertices. So this is what I discard, these kind of graphs. Now here's a theorem that tells you when a particular path of initial values is a good path, basically. You can generalize this theorem. Adler and Veselov also said, well, you don't have to have initial values on a path, but you could also have them on a connected subgraph. This is important. And then there were 2 questions. So there are graphs where you don't have initial value problems on connected subgraphs, and how do you pose a problem that is well defined on such graphs, and whether you have examples of graphs where you don't have initial values on a subgraph but without closed strips. So those were questions that came out of there. And also what I noted was that there is a problem with this theorem, and that was also noted by Adler himself. He had a revised theorem in his second thesis, and that reads like this. So now he has the fact that on your initial value there is a unique solution. There's not a unique solution, but a unique non-special solution. So here is the problem with the first theorem. If you have initial values on a path like this, then according to the initial theorem, there would be a unique solution. But as you can see, there's nothing you can solve directly. You have 1, 2, 3 equations and 3 unknowns. And if you look at that, you get 3 solutions. So it's not unique, the solution on this from this initial value problem. But turns out for integrable equations there is a unique non-singular solution. So that's the statement in the second theorem in Adler's thesis. Here is then an answer to a quad graph where you have a well-posed initial value problem but not on a Cauchy subgraph. So this is the initial value problem, and as you can see it's not connected. And there is no connected initial value problem for this. You can see that this is an initial value problem by just looking at, here we have a quarter of a normal Z2 lattice, which you can solve. And in the sense that these points are all connected here, this is all connected, but this part here is disconnected. There's no blue dot here, for example, to connect this part from that part. Yeah. So here is the deltoidal trihexagonal tiling, for which no initial value problem was known. And here is an initial value problem. The thing is that this initial value problem only works for integrable systems. The reason is we have closed strips, and you need consistency in high dimensional cubes to make sure that this is well posed and you have a unique solution. And you can see that if you think of the three-dimensional cube, the strips on that cube, they close. So that's where the consistency comes in. How to construct these initial value problems? What I did was first remove all the closed strips, and then you can create an initial value problem, or you might be able to create an initial value problem for any equation. And then if your equation is integrable, then you might kind of restore those closed strips. So removing closed strips is basically considering, if you have a closed strip here, you just remove one of the quads, and you say that is now a hole in my quad graph. So then you obtain a non-simply connected quad graph, and there you can use this method to create the initial value problem. Maybe I shouldn't go into all of this, but basically what the method does is you start with a very small part of your graph, and you create a sequence of subgraphs, and in the end you want to end up with an initial value problem on your whole graph. Here's a nice t-shirt. You sometimes in real life you see some nice quad graph on a t-shirt, and there's an initial value. It's a rhombic quad graph, and here's an initial value problem for it. Here's another example where you don't have an initial value problem, and you can see that by looking back at this example here. From those 3 points, you wouldn't be able to uniquely calculate those ones. So if we glue two of these graphs, one on top of the other, then you would get this one. And basically the number of initial values is related to the number of strips. So you need 3 initial values because you have 2 strips here and no holes. So any 3 in the upper part of this graph will maybe, if it's well posed, you would be able to calculate those 3 points here, but then you can't go further and the other way around as well. If you would have your initial values here, you would be able to calculate all of that, but not anything further. And then I've classified the obstructions where you what causes the method not to work, and it's basically for simply connected quad graphs. There's only one constriction, namely that the strips might entangle, and that's defined in a certain way. And you can see some kind of entanglement here. These strips are kind of waving into each other, and that's an obstruction to creating this well-posed problem. For non-simply connected quad graphs, there are 2 more. That has to do with the holes in there, but I think I'll leave it at that, and maybe there's time for questions then.
In the first part of your talk, you were talking about planar graphs generally.
Yeah, in the second part as well.
Yeah, but sorry, I just want to talk about the first part. For non-integrable systems, there's an extra technical condition that I think is probably quite important. Have you considered what happens when the equation is not solvable on one of the vertices?
My whole talk assumes that you can solve for any point uniquely. Otherwise, you won't be able to say anything.
Outside of the stencil, I mean the
Yes.
boundary
Yes.
in is not important.
Yes.
But
So, I mean, if that's not the case, if you have, say, it's quadratic in one of the variables, you get two solutions if you update your map, and the only thing you lose is uniqueness.
but it constrains what initial value problems are well posed.
No, I don't think so. Well, what is well-posedness in that case? I mean, well-posedness, in my view, is a unique solution.
Yes.
Yeah, so in your case, you will never be able to get a unique solution. No, not true? Okay. Well, it's a different problem. Yeah.
I think actually, Peter and Peter, that there are problems where some vertices you don't have linearity in some vertices, but that will just restrict the choice of your the choice of your
Choice
problem.
of the
You have,
direction.
many problems, but there are choices which are still good.
Yeah.
So that's another problem, to do how to make well-posed choice of the problem if we have these extra restrictions of not linearity with respect to certain.
Well, it will then come down to these regions.
Right.
So really,
regions will be
so really these regions that I have for the whole region. Here. So in this region, there's a particular way of updating using a particular vertex. So if that vertex happens to be, you can solve for that vertex, then in this region you would be fine. In this region you might use another vertex. So this is kind of how it works.
Last question. In this Bussiness multi-component quad equations, you cannot evolve the same way in all directions because the edge equations are asymmetric. Does that give you trouble in defining?
No, I mean that would be one example where I would say we have finitely many directions where you would need Gauss problems, and in all the other directions you would have initial value problems. Because I know those systems are solvable with respect to any vertex.
All right, okay, so let's leave it at that.